Hello everyone, welcome to the course on architectural design of ICs. So, we are basically considering the different circuit design, how efficiently we can do. So, the tips and tricks to do the design the efficient circuit, how we can in a easiest way we can do. Okay. So, we have seen in the last class we have seen some of the like this edge detector circuit, how we can implement this, use this multiplexer to implement AND gate, OR gate, that means NAND gate, any other gates, or even the latch, or even the that means flip flop that we have already seen. So, today we will see another circuit where you have been asked to design one, that means clock circuit, which will be multiplied by 2. So, to design this circuit, how we can design the circuit of, that means which will give me the clock signals, which will be, that means the frequency of the clock will be doubled. So, to do that, what we need, that we know that this XOR gate is nothing but the 1 bit comparator. So, at that time what we are doing is that in one of these we have just passed this input clock, in another actually part we have just placed this with one buffers, we have just passed this corresponding clock signals. So, whenever this kind of, that means circuit topology we used, so at that time what is the delay we used here. So, depending on that, so what will happen if I consider, if I draw the corresponding graph of this. So, if this is my clock and at that time, so if I just draw that, okay, this is my clock signals. So, the inverted clock, so the inverted clock will be what? It will be like this. And why? Because there will be some delay which is based on this particular delay. Now, whenever I will XOR these two particular signals, so at that time what will happen? What I will get? I will get for this particular time, that means what is the amount of delay we have provided, that much of time we will get as one single pulse, and then again at this, again we will get one single pulse, at this again we will get one single pulse, at this edge again we will get one single pulse, something like this we will get. So, that means now here what is happening, if this is this I consider as output clock. So, though the output clock frequency will be just double, that means whether if I consider here the period as let us say 10 nanosecond, and if I use that this delay of let us say this 5 nanoseconds. So, at that time these signals will now become of 5 nanosecond, each of these of 5 nanosecond. So, these 5 nanoseconds are means now here I can increase the frequency to twice. Twice means here as this time period becomes 5 nanoseconds. So, at that time the frequency of this particular clock will be of 200 megahertz, whereas in this particular case when this period of this clock is 10. So, at that time this is 100 megahertz. Okay. And here you can see that it depends upon the corresponding this amount of delay, and here you see this is not 50% duty cycle. So, when it will be 50% duty cycle, when this amount of delay is just half of this. So, when this half of this delay is mentioned over here, so at that time these signals will be something like this, again this will be like this, this will be like this, this will be like this. So, at that time that means I will get one particular that means one clock which will be having 50% duty cycle, but it will be having the frequency which is double in this particular case. So, this kind of circuit we can use for multiply by 2. Now, if I ask you to design that how you can design this multiply by 4. Okay. So, then multiply by 4 means again these particular signals, again if you just extend and you put another XOR gate where again you use this. So, for this particular circuit it will be multiply by 4. So, that means whenever we will do or we will add this kind of chain in series, it will be multiplied by 4, then it will be multiplied by here it will be multiplied by 2, then it will again this 4, again if I add, then that will be multiplied with 8. So, something like this, if I add this in series, this correspondingly it will be the multiplication of this clock factor will also increase. Okay. So, any of this in the power of 2, you can just design the circuit in this manner, which will be where the frequency will be just multiplied in the power of 2. Okay. So, and we have already seen that this how we can define this, that means design the circuit divide by 2, that is also very easy. Again we will see not only the power of 2, but the power of something else. Okay. Power of something else means that is whether when that is not in the power of 2, rather than it is like 3, 5, 7. So, how we can design that we will also see. Okay. So, here actually the characteristic of this XOR based multiply, that means clock multiplication, is that the output pulse duration is equal to the delay introduced by the delay element. For duty cycle to be exactly 50%, the delay element delay must be half of the input clock, whatever I just said, and the output duty cycle will, that means the delay element delay must be less than half the input clock period, otherwise it will not work. So, this you can already do, or you can, that means using this kind of technique, now you can extend this circuit to implement any of the function. Okay. So, now then next, suppose we are having, consider another example. Suppose we are having one particular circuit something like this. What is there? We are having flip flop 1, flip flop 2, flip flop 3, and here this is one combinational logic which produce only single wire, which is connected to this another combinational logic, which that means consumes 7 nanoseconds of time, and there in this in between this flip flop 2 and flip flop 3, it is having 10 nanoseconds of time. So, that the time period requirement will be how much? 5 plus 7, 12, but according to my constraint, I just need this T clock should be 10 nanosecond, okay, which is the maximum of this 10 nanoseconds. So, is it possible if I make some changes or in some architectural changes, it is possible to achieve the corresponding clock cycle time of 10 nanoseconds? That means keeping the functionality same. So, all the time whenever we do some kind of architectural modification or some, that means this optimization, but at the time we always have to remember that the functionality will remain same. So, here keeping the functionality same, can I achieve the clock period to 10? So, I can achieve. How I can achieve? As you see, there is, it is mentioned that only one single data wire is basically connected from this combinational, this if I just write this as C1, C2 and C3. So, C1 is basically connected to C2 with a single wire. Okay. So, for that particular reason, as there is only single wire, so what we have did, if we can compute these two in parallel, so at that time I do not have to wait. Actually, here what we are doing, we are finishing this combinational task, and then depending on this, then again we are starting the combinational task over here. But instead of doing that, what we can do, if we can compute this 5 nanosecond and 7 nanosecond in parallel. Okay. So, depending on the two value, one considering 0, another considering 1, means what, as this is the single wire. So, this will be either of 0 or 1. So, from the beginning, if we consider, okay, I just copy this combinational part twice, okay, and here one thing is that I do not have any area restriction, I only have the speed restriction, that means the frequency I need to improve or the speed I need to improve, area requirement is not that much constant. So, at that time only I can do, otherwise I cannot. So, what I will do, I will just parallelly I will compute this 5 nanosecond and 7 nanosecond by what technique. So, this, as this is the single wire, so it may be 0 or 1. As we are doing, actually it is not basically starting its operation. Why? Because it is not getting the signals from 5 nanoseconds. So, once this 5 nanosecond is done, then only it can start its computation, as this is connected in series. So, that is why it always, all the time it actually it will consume 12 nanosecond of time. But what I can do is that I copied this 7 nanosecond combinational, that means C2 twice. Once I compute using 0, once I compute 1. That means, I do not has to wait, that means for 5 nanoseconds computation time to get this value, whether this value will be 0 or 1. So, in parallelly with 5 nanoseconds I have already calculated or compute this 7 0, considering 0 and 1 I have already that means calculating. Then based on this, that means whether this value will be 0 or 1. So, based on this, now I will select which part, that means this considering if it is 0, then if this particular value, that means after 5 nanosecond it finds that okay, this is 0. So, at that time it will select the corresponding path, and if it is finds that okay, this value is 1. So, at that time it will select this and it will go to the flip flop 2. That means, here I do not have to wait for the computation to be completed for C1, and then I can take, or then I can start my processing at C2. So, parallelly with C1 I am doing the parallel computation in C2, and depending on this multiplexers, that means this based on this multiplexers, now I can select that okay, which path I will select, whether I will select with the corresponding computation which is considering 0, or I will consider the corresponding part which is considering the 1. Okay. So, now as I am running these 3 as parallel, so the maximum delay will be here, the maximum delay will be of 7 nanosecond, plus if I say that okay, this is 1 nanosecond. So, 1 nanosecond of the multiplexer delay will be the maximum of this, which is again less than 10 nanoseconds. So, in this particular case, at that time the T max will be of 10 nanoseconds of time, and now I can achieve very easily the talk, that means the cycle time of 10 nanoseconds. In the earlier case or in this particular design, I never can achieve this clock period to 10. I made the architecture changes, and now I can achieve the speed requirement to 10. Okay. So, this is the tricks and this is actually this circuit here, area will be lesser, but here in this case area will be more. In this case speed is more, but in this case speed will be lesser. Okay. So, different architecture, different actually aspects we can follow or we can design. Okay. So, then again we will consider another example. So, this is one of the, that means conventional 4-bit counter. Okay. So, whenever we actually consider this conventional 4-bit counter means actually it counts by, let us say it increase by 1. Okay. So, there will be one, that means there will be these flip flops and the input will be just like, it will be connected like this. Okay. So, the very first is the that means this is the T flip flop, work as a T flip flop, then depending on this it will be also like whenever this particular signals will become 1. So, this will be also like act as a inverter, and then again if this is 1, then again it will be just like inverter. So, this is the basic structure of one counter. So, it says that if I that means if I consider the corresponding critical path, so which indicates this red color signals, this red color paths. So, that means if I increase the corresponding, suppose here for 4-bit I am having this flip flop delay plus 1 AND gate delay plus 2 AND gate delay plus 1 XOR gate delay. So, if I increase it to 5 bit, so at that time again I need another AND gate over here and XOR gate at the very end. So, at that time what will happen? The delay will be increased by another 1 AND gate. That means what? For 4-bit the delay is T clock to Q plus 1 to 2 AND gate delay T and plus 1 T XOR, right. For 5-bit what it will be? It will be remain same plus it will be 3 of T and plus T XOR. In the same manner, if we increase the corresponding bit for this counter, this number of NAND gate will be increased. Okay. So, now consider another example is that in traditional finite state machine we are having something like this, we are having these flip flops and in between them we are having this combinational logics which are placed just in between of the registers. Okay. But whenever we consider the low power FSM or this low power finite state machine, so at that time it is not like this. Here you see the in traditional FSM the clock is basically connected synchronously, it is connected to every of this flip flop. But whenever if I ask you to design one low power FSM, the same FSM, if you have to consider for low power application, so at that time it will not be the same. So, at that time what you have to do? You have to use some kind of enable signals which will be associated with the clock. So, that means you have to here you have to use the gated clock. So, how you can do? So, at that time you are having this that means you are having this clock signals, then again it is OR with the output of some other flops which will be the clocks, and then every of these particular signals will be now it will be all these clocks are now it is gated. Okay. So, how this is gated? Here you see this clock is now it comes with the enable signal. That means whenever this particular clock, that means this circuit is not running. So, at that time, depending on this particular logic, the clock signals will be just 0. If this particular signal, if this particular that means FSM is running at the running condition. So, according to the logic which provides this provides the corresponding enable signal which comes from this combinational logic, they will be OR with the clock. So, whenever this enable signal is okay, this I need that okay enable signal make the clock enabled and it will be running in the running condition. So, at that time every of this flip flop will be connected to the gated version of this particular clock. Okay. So, the same circuit they will be at that time modified to this particular architecture to achieve the low power. So, whenever we are doing that means we are making this traditional FSM to this low power FSM design. So, at that time what we are doing, intentionally we are putting some of the extra hardwares which is in terms of these gates, along with whenever we are putting these gates means what, now the corresponding delay will be also increased. So, that means the speed of this will be also reduced by a factors. So, area is also increased, the speed is also decreased. To achieve what? To achieve a great, that means performance or a good performance in terms of power consumption. Okay. So, this is one of, that means the architecture is been modified in this particular case with respect to power consumption aspects. Okay. So, in the previous example the circuit was implemented with respect to the speed constant. So, in this particular case this particular architecture has been developed in terms of power as a major constant. Okay. So, then this is actually, this says that when this enables will be coming from this particular combinational loop, at that time this enable 1, the clock is gated and it will be activated, and if this particular circuit, that means when this enable is 0, at that time the clock will not be, that means the clock will not affect the corresponding circuit. So, this is one of the example of this. This is traditional binary counter, what we have already seen that. Okay. So, the first is this T flip flop and then we are having this XOR gate, then again it is ANDed. So, this if I just make this traditional binary counter to the low power mode. So, at that time what will happen? This will be comes with this, that means this is one tick B 0, it is, that means all the clocks are now gated and this will be the corresponding enable signals to the clock. Okay. So, whenever this is not running, that means if it is all the portions is 0. So, that means this will be again, this will be also 0, this will be also 0. So, at that time the clock will be just clock to, it will be at that time it will be just nothing but this particular circuit which will be implemented over here. So, some kind of modification in the architecture also, that means in the gates also it is being done to make the corresponding traditional binary counter to be work as a low power binary counter. Okay. So, in case of, actually here if you see that I need one inverter, 2 XOR gate and 1 AND gate, but here what I need? I need 3 inverter, 1 AND gate and 3 OR gate. So, that means I have increased the speed, increased the area, as well as I by putting this clock gating circuit we are also decreasing the that means speed, but we will achieve where we can achieve the, that means enhancement in terms of power. The traditional binary counter now it is converted to low power binary counter. Now, then again another actually very common circuit which is used in digital circuit design, that is sequence detector. Okay. Now, let us consider this, we have to detect one sequence which is, suppose one, that means pulse is coming. Okay. So, we have to, or the data stream is coming. Now, we have to, that means detect that okay, this particular sequence of 1101. So, at that time how can I make the circuit of one this detector which can detect the corresponding sequence of 1101. So, at that time, at the very beginning, what we have to do, we can write the corresponding finite state machine, or we can draw the finite state machine. So, as we are having, we have to select 4 different pattern, that means 1101. So, we will be having 4 different state. Okay. So, the states are S0, S1, S2 and S3. So, at the very beginning it says that whenever we are at this particular S0 state, if it is found that okay, the input bit is 0. So, at that time again it will, because this bit will be 1. Okay. So, whenever this bit will be 1, then only it will go to the next, that means it will try to go to find the next sequence. If it is not 1, so then again it will try to remain, or it will try to check for the next bit. Okay. So, that is why this, if it is found 0, then it will be 0 and the output will be also 0. If this S0 state finds 1, so at that time it will go to what? It will go to S1 state. So, in S1 state again, if it is found in S1 state, it is corresponds to the sequence of 0. So, if it is found 1, then again it will select, or it will again actually check whether the next bit is 0 or 1. So, that is why again it will be on the same state only, it will not change its state. So, at that time if it is found 0, that means there is a match of the which pattern or which sequence I need to detect. So, at that time the 0 will go to, if I find 0, then it will go to the next state which is S2. Then again in S2 if I find 1, then it will go to S3, otherwise this will, this, if it is found that okay, this is the 0, then in S2 if it is found that okay, this is 0. So, at that time what will get, again it will be like 1 0 0, sorry 1 1 0. So, that is not the actually pattern which we need, then again it will start finding from the starting one. Okay. So, then that is why it is again coming back to S0, then again it will start finding 1, then 0, then 1, something like that. So, as in this particular S2, if I find that okay, this is 1, so it will go to the next state which is this S3. So, from S3, in S3, now if it gets that 1, so then again where it will be back? It will be back to S1. Why S1? Because again actually it is already 1. Okay. Then again we have to select this as 1 1 0 1. So, if I write that okay, 1 1 0 1 1, something like this. So, at that time initially it has to start with this, then again if it is not matching, then again it will go to the next, it will consider the next bit, like next bit, like next bit. So, something like this, one by one it will be processed through this particular state machine. So, whenever it founds that okay, this 1, that means all this 1 0 and then 1 and 1, all the sequence found, then the output will be of 1. In all other case it will be just 0. If it is found that okay, this particular thing is 0, so then again it will go to S2, the previous state. Okay. So, now this is the corresponding this, that means FSM for detecting this particular sequence 1101. If you have to detect one different sequence here, so at that time this FSM will be also of different. Okay. So, now once I can develop this FSM based on the pattern which we need to detect, we have to calculate that what will be the corresponding circuit to which will implement this FSM. So, this is for today. Again we will see how to start or how to basically draw the circuit of this which will give me the, which will detect the sequence of 101 in a data stream. Okay. So, thank you.